So our next speaker is Jeremy Bennett of Embecosm, where is the Chief Executive. He's going to talk about how to port AI systems to new computer architectures. Dr. Jeremy Bennett is Chief Executive of Embecosm, a specialist open source software consultancy best known for its work on compiler toolchains and AI. He is the author of the standard textbook, Introduction to Compiling Techniques, published in 1990, 1995 and 2003 by McGraw-Hill. Beyond his technical expertise, he is a passionate STEM ambassador, committed to inspiring the next generation of engineers. He's located in the UK.
Yeah. Thank you, Mike. NVIDIA, with its GPUs and its CUDA software system, has somewhere between 70% and 95% of the world AI market. While that is a technological and business triumph, if AI is to thrive, it needs much more diversity. The question is, how do we achieve that? So I'm Jeremy Bennett, Chief Executive of Embecosm. Today, I'm going to take you through how we can do that. I hope at the end, you will have a good idea how you can create a new chip and get your AI systems running on it. Start with an overview. I'm going to focus on neural networks, and I'm very well aware there are plenty of other types of AI out there, but neural networks is the vast majority of what's driving the industry today. Whatever technology you use, PyTorch, TensorFlow, JAX, Onyx, all of these systems end up representing their neural network as a graph. And the way you do your inference is you walk over that graph, taking inputs. Those inputs are represented as multi-dimensional arrays. That's what a tensor is. It's just a posh name for a multi-dimensional array. And the nodes in that graph tell you what operations to do. Multiply these two tensors, add these two tensors, do a two-dimensional convolution. And so you walk over that graph, executing the nodes with those operations. Where you execute them is governed by the dispatcher, because all AI systems for neural networks are based on the concept of having a host CPU that's a general purpose processor and some form of accelerator. In the majority of systems today, that host is an x86 and the accelerator is an NVIDIA GPU, but it doesn't have to be. If you're going to put new hardware in there, and of course, the one other step in there is you may have some clever compiling work going on to make your neural network more efficient. And that ties in a bit with the first talk we heard about sparse graphs and so forth. If you're going to implement support on a new chip, you're going to have to work out where to change this. And the place you're going to have to fix for new hardware is the dispatcher. What do I dispatch and where do I dispatch it when I have a different accelerator or a different host? There is work you can do at the graph level transformation, but that's secondary. That transformation is not hardware agnostic. It will be making decisions about how to partition matrix operations depending on the size of your matrix multiplication unit, for example. So it's not hardware agnostic, but it's a secondary consideration. I'm only going to focus on the dispatcher today. And this model of computation applies. This is a project we worked on. It's more than 1,000 RISC-V, 64-bit RISC-V cores with a gem unit, loads and loads of gem units on it as well. And in that case, the dispatcher has got a multi-core host and vast numbers of accelerator cores, and it's got to work out how to push the operations efficiently across all that compute power. And you can do it with microcontrollers. And the graph evaluator and the dispatcher is much more simple. It's worrying about one operation at a time. You've typically got a processor and maybe a bit of an accelerator, maybe a DSP or a MATMUL unit, or maybe a specialist convolution operation device. And their standard parts of PyTorch has ExecuTorch, which is the technology that does that. The TensorFlow has what used to be called TensorFlow Lite for micros, now called Lite RT. And actually, a lot of what we do is pre-silicon. When we do our regular compiler work, that's invariably pre-silicon. But this is we did with our big ones. You can do all this stuff actually in simulation. In this case, we had an x86 host, and we were using a QEMU model of the RISC-V cores and using shared memory just to transfer. That isn't going to give you any performance benchmarks if you do it in this particular case, but it did allow us to see if the flow would work, if the operations were coming up with the sort of frequency we expected. I'm going to focus today on high performance RISC for AI and the use of a language called SYCL. Now, we've sort of almost touched on that because the previous talk talked about OpenCL. Just how many people here know about OpenCL? Okay, how many people here know about CUDA? Okay, slightly more, but so CUDA is NVIDIA's GPU programming language. It's an extension to the C programming language with pragmas and a whole API library that understands about massively parallel thread processors. OpenCL is what everyone else uses. It's done by an industry consortium. It's the same age as CUDA. It's the best part of 25 years old. And it's an extension to the C programming language for GPUs, which are usually not NVIDIA GPUs. So obviously, AMD have a big interest in that. Intel have a big interest in it. SYCL is the peer language. SYCL is to C++, what OpenCL is to C. So those two languages. Okay. And if we look inside my graph, you've got the evaluator, and it goes to the dispatcher, and it's got an operation. How is that operation represented? Well, on NVIDIA, it will be handwritten in CUDA, their extension. Now, in PyTorch 2.4, all the main operations, so there are thousands of operations in PyTorch, and same with TensorFlow. But all the 800 or so main operations, there's now a SYCL implementation. That's been since PyTorch 2.4 last October. And those operations have written in a language that understands parallelism. And it compiles. So I've got my operation, my dispatch, how's that operation represented? It's compiled down, it's there as a binary, and it's a multi-architecture binary, sometimes called a fat binary. So it's got stuff that's going to run on the host, maybe an x86, and it's got something that's going to run on the accelerator. In this example, it was an RV64 AI accelerator. That could be running on your FPGA. Okay, so how do you go about implementing this? I've got a new chip. The trick then is it's all written in SYCL. I've just got to get this SYCL running on my new hardware. Well, the compiler exists, that's fine. It's it's a development of the LLVM compiler, so it exists for your architecture. So you compile it, you've got these bindings, but the important thing is then the runtime library, because the interesting thing is not actually the compiler, it's just a simple extension of language, it's the runtime library. Now, even though it's SYCL, which is C++, the actual library boils down to being the same library, the OpenCL library. That's a big API you've got to implement. Okay. Eventually, you will need to implement the full OpenCL library for your new chip, because that's the runtime. But there is a quick trick, which is there is an implementation of OpenCL, which goes down to a simple hardware abstraction layer. It's a bit different to your usual hardware abstraction layer because it's a hardware abstraction layer for a very parallel hardware. And that's called the One API HAL, and I'll come back to what One API is. There's a lot of acronyms here, but One API HAL, that hardware abstraction layer, you can bring that up for your new target, in this case, RV64, in about 3 months. It's specialist work. I mean, it's not just, hey, you're a software engineer, do it, it'll take you 3 months. If you're in this field, it takes about 3 months to do. And once you've got that working, you can get your system going. And it will work. And it'll take each of those nodes as they come through and run it. Now, why might you then want to go and do a full OpenCL library implementation? The problem with the first way with the HAL is it's very much operation at a time, operation at a time. If you've only got a small processor, that's probably fine. You don't need to go any further than that because you could only handle one operation on your chip. If you've got a powerful accelerator, potentially you can do multiple operations at a time. And OpenCL has the concept of computing ahead. Okay, please go and do this operation. Give me a handle on the result. When I need that result, I will come and ask you for it. So you can run lots of operations at once. You can't do that through the HAL. You have to have the full OpenCL implementation. If you've got 1,000 core RISC-V, you're going to need that. If you've got your FPGA accelerator, maybe you don't need to go that far because you've only got five or six cores on there, and you're probably only ever going to do one operation. These operations, I should be clear, they're big operations. If you've got a convolution on a huge tensor, that's going to use your 1,000 cores up just doing that one operation. Okay, but for some of the other operations, you might want to merge them. So all this is facilitated. So the language has existed. It's got a standardization body, Kronos, and everything. But one API was put together. It was originally put together by Intel. Intel realized, even though it was open source, if it was owned by Intel, no one would use it. So they created a foundation that's independent. That's the Unified Acceleration Foundation. Embecosm's a contributing member. A lot of your big names are members of that. The Unified Acceleration Foundation, they contributed all the stuff they'd done, which included this construction kit. They called it One API. It was going to be the One API Foundation, but they thought that wasn't good, so they called it the UXL Foundation. The One API construction kit is all the stuff that goes around the SYCL programming language, the library, and everything that you need to run on AI chips. And the slides will go out. You need a compiler. Well, for most architectures, you've probably got that compiler anyway. And there's a whole load of stuff. All the stuff in white there is generic. You don't have to do anything. You take it. The bits you need to do are the green bits. So you need a compiler. So if you haven't got a compiler for your chip, because you've invented your own processor, like red semi, then you need to pay someone to do a compiler. I can recommend a company. But the other bit you need to do is you need to do that back end. That's where the HAL comes in. We can bring that up, the first version, in about 3 months. You can opt, if you just want to stick with the HAL, then probably over the next year or two, you could optimize it. If you need to do the full OpenCL, that's a big, you're going up against the NVIDIAs of this world. You're going to have to put in the same sort of effort that they do. As you go down the market, as you go further, the runtime is only on the host. You don't have a runtime on the accelerator in this model. But when you go to the full OpenCL API, you're starting to do not just the HAL, but the full OpenCL. You're probably going to start looking at your accelerator, having some sort of monitor, minimalist runtime on there so you can make maximum use of it. So that all comes, that's all freely available. It's all open source. It's not owned by Intel anymore. So what I want to present today quickly is showing this in practice. So Will Jones, my co-presenter, who isn't here today, but who you can hear speaking next week at Bletchley because he's leading the best practice initiative for TechWorks AI. He and I supervise the group design projects for the MSc, final year of the MSc at Southampton University. So we had 6 students last autumn, and we said, make a little demonstrator for us. And I'll just present that to you. Here are the names. They give them. I hope they've gone all shy. They wouldn't give me a photo. So here's this target platform, and it's to demonstrate the process. It's not to beat the world. The host was a Linux PC. The accelerator is a Zinc 7000. So it's got a programmable logic, a general FPGA fabric, and a couple of Cortex A9 cores, the processing subsystem. The way they're going to set it up is to use the Linux PC as the host, a Microblaze 5 as the accelerator, and the ARM core is being used solely as a comms platform between the host and the processor logic. It's not doing anything clever itself. Okay. The benchmark we gave them was ResNet 18. ResNet 18, 18-layer residual neural network. It's an image classifier. you give it a picture and it will tell it's one of 1,000 different possible images. So here's our graph evaluator and then our dispatcher. And we've said we want the dispatcher just to handle handing off 3 operations: add, batch norm, and the conv 2D, the 2-dimensional convolution. Everything else you can just run on the host as normal. Okay. So we gave them that as the goal, the stretch goal. One thing they came back to us and said, it's great. Intel have written SYCL implementations of the 800 common operations, which includes these 3, but we had to rewrite them because SYCL, just like CUDA, you can write in a target specific way. So it was SYCL that worked really well if you were going to go onto Intel accelerators. So they had to make that generic. So that was a good result to know, is you've got a good starting point, but you actually have to do a bit of work up front as well. So the next thing they realized was that even going to the HOWL was going to be quite hard, because they wanted to the HOWL's idea is it compiles down and you eventually get all these binaries and you put them on your target. Whereas they wanted to be offloading really individual topics. So they came up with this concept of an interposer. So here's my multi, and they said, actually, we're going to snip out of the OpenCL library 2 of the functions, which are the 2 of the functions that capture the operation you want to do. And we're going to intercept those 3 operations of interest, and we're going to do clever stuff with them. Okay, and they called that an interposer. So the interposer sits in there, and when it sees the 3 operations of interest, it passes them out to a TCP socket. It goes through the ARM processor, which eventually ends up putting them on the microblades and saying, run this operation on the microblade. Okay, so that's what we had there. Of course, getting that all working on an FPGA grade is quite hard. So they did quite a clever thing, was to say, well, that interposer can send TCP/IP anywhere. Let's just rate a fake Python server just to make sure it all works before we try and put it on the FPGA. And I think that's something when you're designing these systems, the more we do this, the more we realize making sure you've got the intermediate steps that are simulations to make it all working, rather than thinking you can go straight to the hardware, is quite important. So what we've done is, this is the one API, but they've said we can go even quicker. And they only had 10 weeks and they'd never done this stuff before. They were bright lads. We do this every year. This was one of our best teams we've ever had. But even so, just 10 weeks from scratch. And they've got an even simpler version with the interposer, which isn't about properly compiling everything. It's just saying, can I get this work? A bit like I did with the QEMU earlier. Okay, so here's the interesting thing. This is the whole system with the interposer, and I'll give you some data later. They wanted to prove that they really had done portability. They swapped out the Microblaze 5 and put in the Microblaze Classic instead. Completely different architecture. That's all they did. It just worked. Okay, and that suggests, obviously they used a Classic compiler, but I think that was a tribute to the fact that they'd actually nailed the portability. New hardware, I'd change basically one thing, and it just works. So, question is, how good is it? Well, here's the Microblaze Classic. I'll start from the back. Okay, and we didn't get the whole of ResNet 18. It was a structured thing. They had examiners to satisfy, and we said, don't, you also need a Christmas holiday. Write up what you've got, because it's a phenomenal result. Anyway, add 25,000 microseconds, batch norm 100 microseconds on. Okay. RISC-V is an improvement. Goes faster on RISC-V. However, it's a proof of concept of what you can do, because they could have always run it on the host, and of course it goes much faster on the state of the art. The Microblaze is running at 100 megahertz. The host is running vast numbers of cores, optimized. We're not doing all that TCP/IP. That wasn't the point, but we ought to be honest about it. So that project is being marked. I'm waiting until the deal when we supervise it, it's all done in the open. All the repositories there, if you want it, on GitHub. Their dissertation will be publicly available once it's been marked, but it's stuck in the Southampton University marking system. But I will come to what's happening to it in the future anyway. Question is, let's now bring that all together in the last 5 minutes. How do you go about bringing up your own AI tooling? Let's look at what's going on in AI. Millions of people are using AI in the sense that we've all played with ChatGPT and had a bit of fun. And indeed, some of those people on my diagram, you'll see a little silver robots because some AIs are playing with AI. Actually, the interesting bit is this: people using standard models in applications. That's where the real revolution in productivity is going on. There's fantastic stuff going on in making simple things like, I've told some people, conveyancing, taking the burden off conveyancing solicitors to make their job more interesting and more productive. That's the exciting revolution that's going on. They're all using standard models. They're using ChatGPT with standard models. They're using image recognition with ResNet, one of the ResNet varieties. That's the bulk of it. Lots of people doing that, professional software engineers, some of them doing a very good job, and robots doing it as well. The number of people writing new AI models is very small. Okay? People, ResNet, all the ResNet models come from 2015. There's not many people writing novel new AI models. There are a small number of people there, but when they do them, it's a big thing. The whole the large language model architectures, so whether it's Llama or GPT, they're examples up in there. So there's not many people doing that, and some of them, win Nobel Prizes, quite deservedly, in my opinion, for AlphaFold, but that's a small group. But at the top of the pyramid are these people doing AI tools, and there's not very many of us. Okay, that's a bottleneck if you want to bring in new hardware. So how do we help? Good thing is a lot of this is starting to become open. It didn't used to be closely held secrets of what OpenAI, NVIDIA, and the like. ExecuTorch is part of PyTorch, LightRT is part of it. They're freely available, and there's tutorials. The tutorials are good, by the way. Private use one, which is, you may have seen, that was what I used for the QEMU simulation. That's part, but it's been part of PyTorch for years. SYCL OpenCL is part of PyTorch 2.4, and you can get there's where you can get started with it. The one API constriction kit is on CodePlay's GitHub. CodePlay was bought by Intel a couple of years ago, so that's really Intel. This is what's happening to that student project. It's being turned into a full-blown how-to. Now, I'm hoping to get it out in the next few months. I have got to get it out by May because I'm presenting it at the European RISC-V Summit. So that's coming out, and that will be a guide to you. It's a step-by-step guide saying, here's how they did it. So you can pick it up and use it as a starting point for your projects. And if you can't wait to that, you can come and ask me for help. Okay. So, thank you very much. Hopefully that's given you some insight, and you've got an idea of, if you've got a new processor, if you've got a new chip, how you can go about getting AI systems running on it. Thank you.
Okay, in the new system, which is most important, the hardware, the tooling, or the AI platform running on top?
At the risk of being rather boring, all of them. If you get any one of those wrong, you won't have a good system. You've got to get them all right. Actually, people are starting to wake up to the fact that the software ecosystem matters as much as the hardware. You can have the best hardware in the world. If you can't put the software on it, it's not going to be any use to you. I should set some expectations. This stuff is changing super fast. These tools, ExecuTorch is barely over a year old. The SYCL stuff is months old. It's Wild West out there. These technologies come and go, and actually it's very exciting. It's not terribly stable. The technology I've talked about is about as stable as it comes. So I don't want to set over expectations, but I think people are waking up to the fact that you can't just do hardware. You've got your investors have paid for the hardware, but now they want to see results, and you need the software for that as well.
Okay. How long does it take to bring up an AI system to a new chip or accelerator to a level of maturity to commercial use?
So we generally suggest it's probably of the order of 2 years to get to maturity. We can bring it up so you can start using it and testing it and checking it all works with the how in about 3 months. There will be iteration after that. If it's a small system, maybe not so much. So maybe a small system where you've only got a few accelerators, we can get something like ExecuTorch going, perhaps with the HAL accelerator, using it to do it quickly. We're talking 3, 6, 9 months. If you've got 1,000 core RISC-V, that's going to take years to get the very best out of it. Look at what NVIDIA have spent over the last 3 decades getting to where they are. Okay, so I would say that's where you're sitting on. It's a spectrum, but small systems, yeah, you probably got something you'd ship to your trusted, favored few customers, yeah, after a year, perhaps, and probably ready for general availability 2 to 3 years after that. And probably, like all these things, you keep on developing and making them better and better even after you've fully released it.
Okay, and how do you plan on reducing the NVIDIA market share?
It's a big target. I think the place, NVIDIA completely dominate training. Absolutely. I think whenever we engage with customers, they start as startups, their vision is to take on NVIDIA everywhere. Very rapidly, they concentrate on inference. I think inference, there are so many applications where you don't want to put a GPU on. Okay, I think inference is where it will move first. And there is an argument for saying that I have to train a model once, I have to infer it all the time. So there's only so many chips I can sell for training. I can sell a lot for inference. So I think probably NVIDIA will not sustain in the inference space. The training space is interesting. Just look what DeepSeek did with a few tweaks. The stuff that DeepSeek did wasn't new. All the techniques in DeepSeek were known. They just put them all together and showed you didn't need quite so many GPUs. And look, you know, what, 600 billion off their stock price in 48 hours. So, you know, I wouldn't necessarily want to be in the training space.
And the power of the internet, Mark Delinsky of Southampton University just said the student project has been marked. He was a supervisor. The students will get the mark this week, so I can make the project report available this week, subject to consent of the students, and fix a couple of typos. And he's given an email if you want to call MZ or Mark Delinsky at ecs.sutton.ac.uk.
Yeah.
Updates.
Yep. Okay. Thank you, Mark.
Okay,
Much appreciated.
thank you, Mark.
Okay.